Hi everybody. Today I thought we'd have a further look at the electronic DC load project that we've been working on over the last number of weeks. Following on from a lot of feedback and comments you've been making on this project, I decided to have a further look at it with regard to making some improvements both in accuracy and also in functionality. So what I'm going to do today is talk you through some of the changes that we've made to the project. The main printed circuit board, if anybody's following this project and started building it, I'm going to try and maintain the main PCB as it has been so far, and then we'll just add improvements to that, either in terms of changing component types or values, and also we may add additional circuitry. In that case, it'll be a small module that will attach to the main PCB. So let's have a look at the changes that I propose today. Right, well here we see a list of some of the changes and improvements that I'm going to talk you through today, and we'll implement all these and test them out and show you the effect of it on the project. And the first thing I decided to do is change the way we make our input entry to this DC electronic load. At the moment we're using little tactile buttons, which are fine because we only need a few at the moment to select constant current, constant power, constant resistance or the battery option. But as we add more functionality to the project, then we need more buttons. And it gets a bit cumbersome to just keep adding more and more tactile buttons, although it's quite easy to do that. So I've decided to do away with the tactile buttons, apart from the one that's on the rotary encoder to move the cursor position on the input entry. But all of the other functionality will now be controlled by a keypad entry. And I decided to use one of these cheap little 4x4 matrix keypads, which come with a flat wire lead on it as well with a connector, and that will simply plug in onto the main printed circuit board by simply removing the connections now where the tactile buttons plug in, and we just simply plug in the matrix keypad into that connector on the main PCB. And the main changes are then going to be in software to drive the keypad entry for this. So that's the first change we're going to make. The second thing we're going to do is improve the way that the current is measured on this DC load. At the moment, if you recall, we simply sense the current through the 0.1 ohm sense resistor, measure the voltage across that. It's fed in to a op amp which has got a gain of around about 2, and there's a little trim pot on there which we used for calibration of setting the current reading on the LCD display. And I decided to do away with that. So rather than have a manual adjustment for setting the current, the calibration of the current reading, we'll now remove that, and it'll be done automatically by improving the accuracy of how we monitor the current. And again, I'll show you that as we go through these changes. The third thing is that a lot of you were asking about, can we add additional options for different types of batteries to check the capacity of not only lithium batteries but NiCad batteries or nickel metal hydrate batteries or even lead acid batteries. So what I'm doing is I'm going to add another menu screen on there that'll then give us the option to select different types of batteries if you want to check the discharge rate and the capacity of the battery, and that again will be done by using an input entry from the keypad, which is linked to the menu on the display, which I'll show you later. Now the fourth thing here is that we had one or two questions about the accuracy of the reference voltage for the DAC, for the digital to analog converter. That is what is eventually driving the voltage source for the MOSFET. And quite rightly, at the moment we're using the 5-volt supply voltage on the main PCB, which is not particularly that accurate. And one or two of you said, well, could we not use a proper reference source for the DAC? So what I decided to do was have a look at that and add a separate reference source voltage for the DAC, which is more in tuned to the 12-bit DAC that we've got. Remember, the 12-bit DAC has got 4096 steps. So it would be nice if we could have the reference voltage which related directly to that. So I've decided to choose a 4.096 volt reference source IC to feed the voltage to the DAC, which then means that every step that we have of voltage coming out of that DAC is exactly 1 millivolt, so you get a nice accuracy in terms of adjustment of the voltage coming out of that that's eventually then feeding the MOSFET. Again, I'll cover that shortly. This will be on a small additional PCB, tiny little thing. I'll show you how you can do that quite easily, and then that will then be just added to the main printed circuit board. Now the fifth thing is I've added some protection for the op amp. One or two people said, well, what would happen if the MOSFET were to go short circuit? Would it not blow the quad op amp that we have on the soldered onto the main printed circuit board? And that is a possibility, a real possibility. So I decided to improve the protection for that op amp by making some changes to the circuitry, and I'll cover that also shortly. The sixth thing I've got listed here is the zero reading with no load. And what you may have noticed that when you first switch this unit on, you get some erroneous reading, only very tiny, on the actual current, actual voltage, and maybe even the actual wattage readings. So you might get a current reading that's giving you, saying it's 0.006 or 0.002 of an amp, whereas in fact there's nothing connected to it at this stage. So what I have is now an option where you can press a button on the keypad which will zero the display out to all zeros before we even start. So we'll have a look at that as we go through the project. Now, because of all these additions and changes, I had to rewrite the software. So you have the latest version of the software for this project. I've now written the software in such a way which it makes it easier for you to follow through and make changes yourself. So the main loop now of the software is quite small, and it now relates to a lot of little subroutines that it calls during the main loop as it goes round. So again, I may cover off some of those points today or later, but suffice to say, I'll give you a link down below where you can download the latest version of this software. I'm already up to version 8 because I've been doing some work over the last few weeks of making these changes, and it's every time I make one change I think, oh, I can improve that and do something else. So we're now on version 8, and I'll give you, as I say, the link below, and you can download and install version 8 on your project. So they're the additions and changes that we're going to make today. So let's have a look at them now in a little bit more detail and how we implement them onto the main PCB. Here we now have the change in the circuitry with regard to wiring in the keypad. There you see the 4x4 matrix keypad, and the green connector there, that's what we already have on our printed circuit board. That's that 10-pin inline connector which we have some of our tactile buttons plugged into, and we're going to use that for the keypad. Remember, the outer 2 pins of that connector on the PCB go to ground, so we're not going to use them for the keypad. So we're going to use the middle 8 pins, and that's what we'll plug in. I've indicated here on the circuit pin 1, 2, 3, 4, 5, 6, 7 and 8 of the keypad, and that relates to that connector there on the keypad. I've indicated where pin 1 is on the left hand side, so pin 1 down to pin 8. So 1 to 3 are the rows and 5 to 6 are the columns. So that's row 1, row 2, 3 and 4, and the columns, first column is pin 5, second column is 6, and so on. Now you may also recall that originally the cursor button on the rotary encoder was going to D5, data pin 5. Well, as we're now using that for the keypad, we now have to use another pin for the cursor button, and I'm using one of the free analog pins, in this case A3, analog pin 3, which is equivalent to a digital pin 17, and you'll see that reference on the software when you look at the software. So A3 goes to the cursor button, and that works as normal as we did before. Nothing changes with the rotary encoder, that remains exactly the same. So there we are, that's the simple changes, and we'll have a look at how easy that is to do in a moment. We're going to now replace the tactile buttons here we have plugged into the connector on the printed circuit board with the keypad, and so the first thing is just simply unplug the buttons from the pins on the main board. That should come away quite easily. So we just remove that from the board, discard that. So now we're left with the empty pins, apart from the second one there. That's the one that's going to the button on the rotary encoder, and we need to remove that as well and then reposition that onto A3 on the Arduino Nano, and I'll show you that first. So we're going to just simply remove the the lead from that socket there, so I'll just unplug that. And what I've done, if you look now, you'll see on the Arduino Nano I've soldered a pin onto A3 on the Arduino Nano, on that pin there. That's just soldered onto the board, so we can now plug into that pin. So the button is now reconnected and it's now going to A3 on the Nano. So the next thing you do is we're going to plug the keypad in into the pins there, ignoring the first and the last pin. And remember that the keypad needs to be facing you when you're plugging it in. So we plug the keypad in. The keypad is now plugged in. I've left the outer two pins free. I'll just zoom out and you'll see how that's all connected. So there we have the keypad now connected with it facing towards you. That's the correct orientation. Well, I'll just quickly mention the functions on the keypad. The A button is constant current, the B button is constant power, C is constant resistance, and D is for the battery capacity mode. The hash key will be the load on off button, and the star button there is going to be the 0 button at switch on if you want to use that. Now the next thing we're going to have a look at is the changes that I've made to protect the op amp in our project in the event of the MOSFET going short circuit. Now these days most op amps and ICs for that matter have some form of internal protection in the event of static discharge on the input terminals. That's sudden high spikes of voltage on the input terminals. And the way they do this is quite simply by using a few clamping diodes internal in the IC to clamp the input voltage to either the supply voltage or ground. Now I've just illustrated that here and I've shown these clamping diodes on the plus input terminal, but you'd have equally the same circuitry on the negative terminal as well. But you can see quite clearly from this is that if for any reason we get a sudden high voltage spike going to the input of that op amp, then as soon as that voltage goes higher than, in this case, the plus 5 volt supply voltage, then that clamping diode would switch on and simply clamp the input terminal there to plus 5 volts and so protect the IC. If it spike was to go in the opposite direction, the other diode would do an equally good job at protecting the IC. Now under normal conditions, the electrostatic discharge spikes that you get are just for a fraction of a second, and therefore you only have current flowing through that diode for that fraction of a second. Now if you look at the data sheet for that, the maximum amount of current that that diode can sustain over a long period of time is around 5 milliamps. So we need to make sure that we don't exceed that current going through that diode, otherwise you blow the diode and you lose all your protection, you damage the IC. So if we take our particular circuit where we have, say, 30 volts load, if the MOSFET were to go short circuit, then what you'd find is at that point there you would have 30 volts. That 30 volts is fed straight onto the plus terminal of the op amp. As the input bias current of the op amp is in picoamps, very low, you get virtually no drop across that input resistor there. But then all of a sudden the clamping diode sees that 30 volts and switches on and clamps the input voltage to, in our case, 5 volts. So that we have plus 5 volts there. Now that means that across that resistor, the voltage across that resistor is now 25 volts. And that voltage is going to be constant because the MOSFET's gone short circuit, it's going to be there all the time. So if we do the maths on that, the current now flowing through that diode inside the IC is going to be I is equal to the voltage divided by the resistance. We know the voltage is 25 volts, and we know the resistance, in our particular case at the moment, we've got a 1k resistor there. So we've got 1k. And if you do the maths on that, then you'll find that that will give us 25 milliamps. So if we had that scenario where the MOSFET went short circuit with a 30-volt load, then you'd suddenly have 25 milliamps flowing through that clamping diode in the IC and probably blow the diode because we've exceeded the 5 milliamps maximum. So the simple solution to this is to change the value of that resistor. So if we change the value of that resistor to 10k as opposed to 1k, then if we now do the calculations again, if we replace the 1k there with a 10k resistor, then you'll find that the maximum current flowing through the op amp in this case is now going to be 2.5 milliamps, which is well below the 5 milliamp maximum of the clamping diode. So simply changing the value of the input resistor, increasing the value of that, would give us our protection in the event of the MOSFET going short circuit and effectively control the current flowing through that clamping diode to a safe level. Now that's just one part of what I'm going to do today, but at least it illustrates the point. Here we now have the actual changes that I've made to the circuit of our project to give us that protection in the event of the MOSFET going short circuit. And all we've simply done is we've replaced those two resistors which were previously a 1k resistor, that's R7 and R16, which went to the input terminals of the op amps, and that gives us the protection in terms of damaging the internal clamping diodes inside the op amp. And in addition to that, I've also added a diode clamp across the 0.1 ohm sense resistor. I'm using a fast acting diode, the UF5408, and that normally has a forward bias voltage of around 1.7 volts. So if the voltage there gets to 1.7 volts, that diode conducts and takes that point then down to ground. Since the MOSFET is short circuit in this particular scenario, then I've got a 5 amp quick blow fuse there which would then immediately blow. So that's the overall protection now I've added to the circuit in the event of the MOSFET going short circuit. Changed the value of two resistors and added a diode and a fuse. I now want to have a look at the changes that I've made to when we measure the current flow through this DC load. Remember that we're monitoring the voltage across that current sense resistor, that 0.1 ohm resistor, to give us an indication of the actual current flowing through the device. And if we've got 0.1 ohm there, if we had say 3 amps flowing through that on the load, then that would give us 0.3 volts. But if we said that at a later stage we wanted to increase our cables to up to 5 amps, then that would give us 0.5 volts. So I think for this project the absolute maximum current we'd ever want to have through the sense resistor would be 5 amps, so we'd say 0.5 volts is our absolute maximum sensing voltage at that point there. Now what's happening is we're feeding that 0.5 volts, and the original circuitry simply amplified that voltage with this op amp here before feeding it into the ADC. And we had a little trimming pot there, RV1, which we adjusted to calibrate the current as displayed on the LCD display. Now what I want to do in the changes for this part 3 of the project is to remove the need to calibrate this. So rather than have a amplifier here, I'm going to convert that into a buffer, and you'll see the reason for that in a moment. If we convert that into a buffer, then we have no gain on that stage, and therefore that voltage that we sense across that resistor will be fed straight into the ADC IC. But the interesting thing about this IC is that inside the chip itself, there you've got a programmable amplifier, and that programmable amplifier can be programmed to have a gain of ×1, ×2, ×4 or ×8, and we can program that in software. So I'm going to use that capability now to amplify the signal coming from the sense resistor rather than using this op amp here to amplify it at that point. So what I'm going to do is simply convert this op amp into a buffer by removing these two components here and that component there. So remove these two resistors and that preset, so we get rid of those components. And then we're simply going to now connect the output of the op-amp back to the input, so it now acts as a buffer. So there's no gain over that stage. Now the advantage of a buffer is it has a very high input impedance, so it would have no influence on the voltage we're measuring there anyway, as it did before, but also the output impedance would be low, which is ideal for the ADC IC. In order to compensate for the fact that we now have no amplification there, I'm going to set the amplification in this ADC IC to a factor of ×4. So we're now going to multiply the gain of the signal coming in by 4, and the reason behind that is that this is a 16-bit ADC, but the reference voltage inside the IC itself is only 2.048 of a volt, which means that the codes that we can use, the steps up and down, can go between minus 32,768 to plus 32,767. So it's swinging positive and negative, but that assumes that you were to use this use the differential input on the input, plus and minus there. But we're only using the positive input to measure this signal, and we've grounded the negative input there, which means that we only can use half of that code. So we're only using 32,767 steps of this ADC to measure our voltage. This means that the maximum number of steps from 0 volts to 2.048 volts is that number of steps, and to utilize that resolution to measure our voltage, remember we said that the maximum voltage we'd have here at 5 amps would only be half a volt. If we multiply that by 4, as I've done here, then we get up to 2 volts, which is very close to the 2.48 volts reference inside the IC. So in that respect, we're using the majority of the steps, the resolution of the steps from the ADC to measure our voltage. So we get a much more accurate indication of the voltage, which we can then display on the LCD via the Arduino Nano. So that's the changes that I've made to the project, and in order to do that we've simply removed 3 components, and in software we program the programmable amplifier inside the ADC IC to give us a gain of 4, and I'll show you that on the software. Here we have the routine in the software that is used to monitor the actual voltage reading and the actual current reading using the ADCs. The top part there is looking at the voltage, and the bottom part there is the ADC that's looking at the current. If we look at the bottom part there, you can see that there we've got where we've set the gain to 4, and that's written there in software. The voltage one is still set at a gain of 1, but we may look at that later as we decide to have a look at some better improvements on calibrating the voltage as well. But for the moment we leave that gain of 1 for the voltage and a gain of 4 for the current, and that's setting the gain of the programmable op-amp inside the ADC. Here we see now on the printed circuit side of the board, I've removed the resistors associated with the op-amp, which we're using to monitor the current across the 0.1 ohm resistor, and I've removed the resistors in the feedback loop of that amp, and also removed the little preset trimmer. So you can see now we've got holes there where the resistors came through before, and in that position there, that's where the trimmer was. That's been removed as well. So there's 2 resistors and a trimmer being removed from there. What we now need to do is we need to connect the output to the input of that op amp to make it act as a buffer, and what we're going to do now is we're going to simply connect the last 2 pins there, pins 14 and 13 of the IC, and I'm going to simply do that by putting a solder join across them last 2 pins there. There you see now I've just bridged those last two pins there on the op amp there, that's pins 14 and 13, just by bridging it with some solder. So that's all complete now. Now the other change that we've made to the project in part 3 is to, instead of supplying the 12-bit DAC from the 5-volt rail, we're going to disconnect it from the 5-volt rail and instead feed it from a reference voltage from an IC, a reference IC, giving us precisely 4.096 volts, and these will equate exactly to the 4096 steps of the digital to analog converter, which means that each step now will be exactly 1 millivolt, improving the accuracy. And to do that, we're simply going to use a small IC, a little surface mount IC, the REF 5040, and very few components required really. We're not even going to bother trimming it. The accuracy is still quite good without any trim, and we just need to add two capacitors. I've added a 1 microfarad capacitor on the input supply to the reference IC on pin 2, and the output we've got a 10 microfarad capacitor on the output on pin 6 before feeding it then to supply the DAC on the VDD line. Now for these two capacitors here I've chosen tantalum capacitors, and the reason behind that is that these reference ICs work better if you use capacitors that have got a low ESR, and a tantalum capacitor has an ESR level which is usually sometimes 10 times better than you'd get with a normal electrolytic capacitor. So that's why we've chosen tantalums there. All of that's going to be mounted on a small little PCB, which I'll show you, and then we'll mount that onto the bottom of the printed circuit board. We'll cut the track to where the supply currently goes to the 12-bit DAC, and we'll wire this in between the two parts on the print, and I'll show you that shortly. But let's have a look at the components and the little PCB that we're going to use for this particular edition. Now to mount the small reference IC, I'm going to use one of these little adapter PCB boards here, which convert from a SMD to a DIL connector. You can buy these blocks of boards on eBay quite easily. I'm just going to break one off of this, and we're just going to use one of those to mount our surface mount IC on. Now if you're using one of these little surface mount converter PCB boards, take note of the wiring configuration. You've got a little white dot there on the board, and it means that that pad there is pin 1 of the surface mount IC when you position it on that board, and then the holes down the side, the DIL connectors, pin 1 is marked with the digit 1. You can see it just about there. So that's pin 1, 2, 3 and 4, 5, 6, 7 and 8. So just bear that in mind when you're wiring up the IC. Right, well here we are now with all the components mounted on that little PCB adapter board. The two tantalum capacitors mounted on there, just soldered onto the DIL connector holes there, and then I've just soldered a few flying leads there, which we'll then use to tack it onto the main printed circuit board. Right, well here we now see the underside of the main printed circuit board. I've just got a close-up there of the 12-bit DAC IC, little tiny chip you can just see on the board, just see there, and that pin there is the supply pin, the voltage supply pin for the IC, and that is the normal 5-volt supply. I've just simply cut the print from that point there to that point there, just cut that track. So we're going to solder the output from the 4.096 voltage reference IC to that point there, and the input is going to go to that point there, and then we simply need to just ground the other side, which is around here. Now in order to mount this little PCB onto the main printed circuit board, I've added a small piece of double-sided tape there. You can see that padded tape there, sticky on both sides. So I've just stuck one side onto the bottom of that little PCB, and then I can peel off that backing and stick it onto the main printed circuit board. So I'll do that and come back and show you that. Well, there we now have the little module mounted on the back of the PCB with the double-sided tape, and you can now clearly see that there's the supply pin for that DAC there. We're going to wire that point there up to that point there. That's the input voltage at that point, and that will go to there, and then we just need to take that point there to ground. So let me put the wires in and we'll come back and have a look. Here we now see the reference module mounted on the main printed circuit board using that double-sided sticky pad that I used to isolate it from the main PCB, and I've wired it up as you can see there. We've got 3 wires coming from the module itself. There we've got the 5 volts going to that point there. There you've got the 4.096 reference coming out and going to the DAC, and then the 3rd wire is from that point there, which is the earth return, and that's just soldered onto the chassis. Okay, so that's the reference voltage all mounted. Just be careful when you're soldering near the DAC. It's very small, that IC, and if you're not careful you could short out the pins by solder spreading across the contacts there. So be careful of that and check it before you switch the unit on. Just look with a little magnifying glass, make sure you've got no shorts around that area there. Now, one other minor change I've made on the project is to change the values of this little divider network. If you remember, we had what I said was a divide by 10 network, which was on the output of the DAC to drop the voltage down. But unfortunately, the 2 resistors I chose at the time, I had a 9.09k and a 909 ohm. I chose them because I had them available and they were very high tolerance and low temperature coefficient, so low drift. But unfortunately they don't give me exactly the divide by 10 that I required, and what I did originally was I corrected for that in software. But what I'm going to do today is replace those 2 resistors with the correct values of 9k and 1k. I managed to get hold of those resistors, also of low tolerance and low drift. So we're going to replace R6 and R14. R6 will now be a 9k resistor, and R14 will be a 1k resistor. So that's the other change that we've made today. Now, if you find it difficult to get hold of those resistors, you could use an 18k and a 2k resistor, but try and get a 0.1% if you can. Now, I'll just point out a couple of variables at the start of the software regarding the calibration. We've got the set current calibration factor there. I've now set that at 1 because I changed the way that the current is now monitored, so we don't need to add a calibration factor on there, so we just simply multiply it by 1, so there's no change to that. But the DAC calibration factor is currently set at 1.01. Now I've managed to get that virtually down to a factor of 1 by adding that 4.096 volt reference for the DAC, and also changing the resistors in the divide by 10 network that I explained. But if you wanted to stick with the 5 volt reference rather than the 4.096, then you'd have to just adjust that factor there to correct it on your reading. Right, well, let's now demonstrate the operation of the DC load, all these changes that we've made and the keypad connected. So I'll just power up first of all. So at switch on we get the usual screen, but now we've got software version 8, and it defaults to constant current mode after the intro screen, and you'll see there that we've got a slight reading there, erroneous reading of 0.002 amp and 0.009 of a volt, and we can now zero that out by pressing the star button on the keypad. So if I press the star button, we can zero out that, so it's all now zeroed. So what I'm going to do now is switch the power supply on. I've got a power supply connected, and I'll switch that on. I've got it around about 5 volts at the moment, So you can see now on the display we've got a reading of 5 volts. You've got virtually no current really at the moment, just a 0.005, it's just some leakage there. And you'll see at the top there it says the load is switched off, we're in constant current mode, and the temperature on the heatsink is 16 degrees C at the moment. Now to turn the load on, we use the hash key on the keypad. So if I press the hash key now, so pressing the hash key, you can see there now that the load is now switched on. At the moment it's set at 1 amp, and you can see there we've got an actual reading of 1 amp, just over 5 volts going in, and there's the wattage calculated. I can switch the load off again by pressing the hash key. So the load is switched off, and we can go to the rotary encoder and increase the current, say, to 2 amp. And if I then switch the hash key again, we can switch the load on. So we've got 2 amps there, and you can see now we've got 2 amps set, 2 amps out, and there's the voltage going in. What I'll do, I'll increase the voltage input, and you can see that change as well as the wattage, but the current should remain constant. So as I'm increasing the voltage, I'm going up. There we're just over 10 volts now and 21 watts. I've set the limit at the moment for 50 watts on this, as we had on the previous version. So that's constant current mode. Now I'll just take the voltage back down to around 5 volts for the moment. That's in constant current mode, and if you then switch from constant current mode to one of the other modes, it also switches off the load as a safety precaution, and at the same time it zeroes the set current. So if I press the B button here, which is for constant power, so you can now see I've pressed the B, we've got constant power now, so we can now set the watts. As I say, it zeroed the watts to start off with, so if I adjust the rotary encoder now, set it, say, 11 watts there, and if we now switch on the load again by pressing the hash key, see the load is now on, and you can see the wattage there. The actual wattage is also 11 watts. So you can disconnect the load simply by pressing the hash key, so it toggles on and off, but if you change mode, it automatically switches it off as well as a safety precaution. If we now press the C button, this is constant resistance. Again, it turns the load off, it zeroes the set resistance there, so we can increase that, say, to, use the rotary encoder, take it up to say 10 ohms, and again by pressing the hash button we can switch the load on. So that's constant resistance mode now. Now the final option is the battery capacity or battery discharge function, and we're using button D on the keypad for that. So if I press that, this time what you see is we get a menu screen for different types of batteries. So we've got LiPo lithium ion battery, Li-Fi battery, NiCad and nickel metal hydrate battery there. We've got zinc battery, we've got lead acid battery there, and then we've got an exit button if you want to go back to the normal routine. So if I were to now press, say, number 1 on the keypad, it'll select LiPo. If I were to select 3, it would select NiCad. So let me press button 1. It then gives you a brief indication of what you've chosen and what the cutoff voltage is before going to the screen to do the discharge rate. So now we've got the load on the battery is off. There's the voltage at the moment. The current is set at 1 amp. And if we now press the hash button to switch the load on, then you'll see it'll start discharging the battery and calculating the milliampere hours. So I'll press the hash button. So you can see now that we're discharging the battery, the timer is going, and also it's calculating the running total for the milliampere hours. And it will carry on doing that until it reaches the cut-off voltage for that particular type of battery. It will then stop and hold that reading and give you that final reading. You can pause it by pressing the hash button. I'll do that if you wanted. Press the hash. We can pause it by taking the load off. It pauses the reading so far at the bottom, and pressing the hash button again will continue it from where we left off. Now if I take the voltage now down to below its cut-off voltage, so let's take that 5 volts down now. We need to take it down below 3 volts. And as soon as we go below 3 volts, you can see there that the load is now switched off, and that's our final capacity reading for that particular battery that we're testing. You'll also notice that next to the set current reading there, it's indicating on the LCD the type of battery you're testing as well. So let's just press the D button again and choose a different battery. So let's press D. We go back to that menu screen, and let's say this time we select the NiCad battery, number 3. Tells you it's NiCad and what the cutoff voltage is. It then goes to that screen, and we can follow the same process again. I'll press the D button once more, and this time I'm going to press the 6 for exit. So we press 6, and that'll take us back to constant current mode if you wanted to go back from that position. Now if you wanted to change the cutoff voltage variables that we've set in the software, you'll find them at the start of the software program. If you look through all the variables there, and you'll see you've got a number of lines there which are giving the cutoff voltages for the different battery types. And I've just set them at the moment for the LiPo battery at 3 volts, the Live-V battery I've set at 2.8 volts, the NiCad battery I've set at 1 volt, the zinc I've set at 1 volt, and the lead acid I've set at 1.75 volts. But those variables can be changed, so if you want to play around with those, you can change those in the software and then just load them back up again. Just load the software back up again into the Arduino. Well, I think I'm going to leave the project there for today. What I will do is put you a couple of links down below. One with the software. You can download the latest version of software, now version 8. And bear in mind that that uses a new library. It's a keypad library, but I give it in the comments on the software where you can download that from as well. The schematic diagram will also be included down below. You can download the latest version of that, and that'll not only include the real-time clock module and the voltage reference module, but also all the changes that I've made to the circuit, and in particular as well the 2 resistors that we changed in the divide by 10 resistor network. Now in part 4 of this project, what I want to do is have a look at 1 or 2 other things, such as trying different types of MOSFETs, and also try to make some further improvements to the project as we go along, which could include things like the automatic calibration of the voltage reading, and improve calibration a little bit further if we can. So let's save some of those then for the next part of the project. In the meantime, if you found this of interest, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.